For this forces video, we're going to go through 3 separate problems. Each of these problems will be a bit more in-depth, and we'll go through a couple of things that I want to emphasize. So for this one, you'll notice that it is very similar to the last problem from the last video, except that rather than the wires coming straight down, the wires are both at the same angle. And so, let's go and get started with this one. We always start by drawing a free body diagram first. And so let's go ahead and draw a box for us. And I'll just put this one over here. And we are told that this box, or this sign, is also 11 kilograms. And so we can put 11 kilograms in the box. And we can go and start filling out what we know. So we know that if it's 11 kilograms, we know that it's going to have a mass, a weight that goes down. We also know that we have 2 cables, so we have 2 tensions that are going like this. And we know that these are each 41 degrees. Now, on our free body diagrams, we want it to only have perpendicular vectors, so meaning vectors that are only going straight up and down and straight side to side. And so when we get vectors that are at an angle, we need to break it up into its x and y components, similar to the vectors that we did before when we were talking about projectile motion. And so this will be your first free body diagram, but it won't be your last for this particular problem. And so, to continue with this problem, we draw another free body diagram. And let's go ahead and get rid of that. So with this free body diagram, we go ahead and draw on the ones that we know. So if that's 11 kilograms, we know that the weight here is going to be 110 newtons. And that's based off of the mass times gravity, which 11 times 9.8. Now, for each one of these vectors, we want to draw them out separately first so you can see what I'm going to do with them. And so what you see here is the triangle, and this is going to be our force of tension. The other thing that we can notice is because they both have the same angle and they're from the same spot, we can assume that they have the same tension in each one, and the x and y components will be equivalent, and you'll see what I mean by that in just a moment. And so this is 41 degrees, and so if we're looking for the x component here, we just do ft cosine 41 because this is the adjacent, so we use cosine, and for the y component we use ft sine 41. And this will be the y component. So let's shrink that a little bit so you can see that there. And so this will be for this vector on the right. And the vector on the left actually will be exactly the same. So let me show that to you as well. Let me move this down a little bit. If we were to draw the other vector that's non-perpendicular, like that, you'll see that the triangle looks very similar. And this is also Ft, the force of tension. And again, we have this as 41 degrees. And so the x component is, again, Ft cosine 41. And our y component is, again, Ft sine 41. And let me put this like this. There you go. Now, what is important to pay attention to in this particular case is that the x components are going in different directions. So one is going to the left, one's going to the right, but their y components are both going straight up. In fact, once we resolve our non-perpendicular vectors into its x and y components, we can just put the y components where they need to be, like this, and put our x components where they need to be, like this. And let me move these out of the way. And now you can see what our free body diagram becomes. And these should be roughly the same. And these, actually let me ungroup now. This will be Ft cosine theta. This one will go there. And this one goes there. And I'll just put this one over here. And there we go. This is our free body diagram. We have Ft cosine 41 going to the left. We have Ft cosine 41 going to the right. We have Ft sine 41 going up. And then we have Ft sine 41 going up as well. And we have 110 newtons going down. From this free body diagram now, we can make our summation equation. And so we begin like this. Let's start in the x, because that's going to be easier. So we can say the sum of all forces in the x is equal to, and we'll go ahead and set to the right and up as our positive directions. So we can say Ft cosine 41 minus Ft cosine 41 is equal to 0. This 0 tells us that our object is in equilibrium. And in this case, we know that our sine is standing perfectly still, and so we should be in equilibrium in both the x and in the y. So that's why we're setting them to 0. And so this simply shows us that our Ft cosine 41 minus Ft cosine 41 is equal to 0. Now we work in the y, so we can say the sum of all forces in the y is equal to, and if up is our positive, we have Ft sine 41 plus Ft sine 41 minus 110, and that's going to be equal to 0. From the second summation equation, the sum of the forces in the y, we will be able to figure out what the force of the tension is. In this case, we can go ahead and move the 110 over, and we can combine these two. Since these two are the same, we can say that's equal to 2 Ft sine 41 is equal to 110. From here, just to show you the algebra for this, we can divide by 2 sine 41, so this becomes Ft is equal to 110 divided by 2 sine 41, and that gives us a force of tension of 67 newtons. There you go. This was to emphasize how we can break up our x and y components from our non-perpendicular vectors. Now, the next problem. A person pushes a 15 kilogram lawnmower at a constant speed with a force of 77 newtons directed along the handle, which is at an angle of 4.0 times 10 to the first degrees to the horizontal. Draw a free body diagram showing all the forces on the mower. Calculate the normal force on the mower, and then calculate the force the person must exert on the lawnmower to accelerate it from rest to 1.2 meters per second in 2 seconds, assuming no frictional force for this part C. So, when we read this, lawnmower is 15 kilograms. We have a constant speed, force of 77 newtons, directed along the handle, which is at an angle of 40 degrees to the horizontal. So, let's go and start drawing our free body diagram. So we start by drawing our square. We know that this is 15 kilograms. Right. Yes, 15 kilograms. And so we know automatically that we have a weight going down, W equals mg, that we are going to have a normal force going up. And if you first draw this like this, that'll be fine. You can think of if this were the lawnmower that you're pushing down on the handle at this angle, like that. In this case, what we want to do though, once you initially draw this, you want to go ahead and draw another free body diagram. We want our vectors to begin from the box, and so we can go back to this. This is the weight, this is the normal force, and this will be our applied force. All we are doing is we are moving this down to this side. But again, if this is how you want to start out the problem, that's fine. Now, once we have this vector, we come to realize that it is non-perpendicular, which for us, again, means we need to break it up into its x and y components. This vector, let's just use this one right now. This vector is measured from the horizontal. And so, if we were to draw the other components, it would look like this. And we know that this angle is 40 degrees. So that is 40 degrees. And this hypotenuse, we are told, is 77 newtons. Now, from here, we can break it up into its x and y components. We know that the x is going to be the adjacent, so we can say that the x component is 77 cosine 40, whereas our y component is the opposite, so we use 77 sine 40. And now we can put these vectors onto our free body diagram, onto our next free body diagram. So we can scoot these over, and we'll go ahead and just bring in another one of these. And now we can go ahead and put these vectors on, one to the right, one going down. These are from the force vector. We still need to add our weight, which is going down, and we have our normal force going up. So let me go ahead and label these for you. This will be our normal force, and this is the force of the surface pressing back up. This will be the 77 cosine 40, and that is from the applied vector. This one down here will be 77 sine 40, and then we'll also have the weight, which is the mass times gravity, which will be for us 15 times 9.8, which is equal to 150 newtons. And there we go. So, calculate the normal force on the mower. So we're looking for the normal force on the mower, and in this case that means we're looking for Fn. If we're looking for our Fn, we can use our summation equation to find that. And so we use the sum of the forces in the y, and we'll go ahead and set our up direction as positive. So we have our Fn minus 150 newtons minus 77 sine 40. And that should be equal to 0. And this tells us that we are in vertical equilibrium, which simply means that the force normal is equal to these two going down, which means that our lawnmower is not accelerating into the ground. It's also not accelerating up into the air. And so when we work out 77 sine 40, this gives us 49 newtons, which means Fn minus 199 is equal to 0, which means that your force normal is equal to 199 newtons. With 2 sig figs, that makes this 2.0 times 10 to the second newtons. And there you go. That's it for part B. Now for part C, calculate the force the person must exert on the lawnmower to accelerate it from rest to 1.2 meters per second in 2 seconds, assuming no frictional force. And so we start listing out our variables. We know that our initial velocity is 0 meters per second. Let me go and just put a mark there. 0 meters per second. We know that our final velocity, that is told to us, is 1.2 meters per second. We know that our time, is 2 seconds. And now, what we are asked to find is calculate the force the person must exert on the lawnmower to accelerate it from rest to that rate. Okay, so we are looking for the force. And now we need to figure out how to relate our force to these other variables, our V0, our VF, and our T. We don't have an equation that can figure this out directly, and so we have to think of our force equation first. So we know that we have F is equal to ma. And so if we're looking for a force, we have our mass, which means we need to find our acceleration first. And from the information given, we can find our acceleration. And so we have Vf is equal to V naught plus AT. So 1.2 is equal to 0 plus 2a. So that means your acceleration is going to be equal to 0.60 meters per second squared. And this is going to be your acceleration. Now, what we have to be careful of here is that the force that we apply is going to be at this angle, at 40 degrees. And so when we are working with this, when we find this initial force, this is going to be in the horizontal direction. And so because this acceleration is in the horizontal, that means that this force must be the horizontal component. And so let's find the x component of the force, which is going to be equal to 15 times 0.6, which gives us 9 newtons. But this is not the answer to the problem. This is only the x component. We need to think back to at the very top when we made this into its x and y components. Think of this as we just found the x component, and now we need to find the resultant. And so we know that this is the x component. And if we say that this is the force that is applied, the x component was given by cosine 40. That is going to be equal to 9 newtons. So the force times cosine 40 is equal to 9 newtons. And again, this is because 9 newtons was the sum of the forces in the x, because this is accelerating in the x. So from there, we can get our force applied. So our Fa is going to be equal to 9 divided by the cosine of 40, which gives us 12 newtons. So this is what our answer will be for this problem. 12 newtons that are applied at 40 degrees along the handle. And again, this is assuming no frictional force. Alright, for this last problem, the helicopter is ascending vertically with an acceleration of 5.00 meters per second squared. The helicopter's mass is 1.30 times 10 to the 5th kilogram, and the person is 50.0 kilograms. Find the tension in the cable and the upward force on the helicopter blades. So what we're looking for, if you look at this picture, we're looking for this tension in the cable, and we're looking for the upward force along the blades, and we'll call this the lift. This is going to be one of the first problems that we have two objects with different masses that are connected together. And so we draw two free body diagrams, and we'll go ahead and say that this first one is the helicopter, and this one is the person. And now, we go ahead and put the weights on both. In this case, the weight is the mass times gravity, which is going to be equal to 1.30 times 10 to the 5th kilograms times 9.8. For the person, I believe it was 50 kilograms. Yes, 50 kilograms. So it's going to be 50 times 9.8. And that means that this is going to be equal to 127,400 newtons. And this is going to be equal to 490 newtons. So let's go ahead and move these out of the way. And so now we just have the weights. And let me put newtons over here. So we've added the weights. Now we need to start adding the other forces. if we think of this cable that's attached to the helicopter, there's a tension in the cable and it's pulling down. And so we have this going down, and this is going to be a tension. So we just say it's T. And if we look at the human now, the person is holding onto the cable, and the person is pulling down on the cable, but the cable is pulling up on the person. And so the rope is pulling up. And because of Newton's third law, we know that these two tensions, these T's, are the same. What we also have on the helicopter now is this lift, and so that is going to be going upward in this case. So we know that this is the lift. And these are our free body diagrams. In this case, we don't have any x components, so we don't even have to worry about it. And so now we can write out summation equations for both of these. So in this case, we know that this helicopter is accelerating at 5 meters per second squared. This will change our summation equations. And also, well, let's go ahead and write this out. So in this case, we know that we have an acceleration going up, which is 5 meters per second squared. And so, why don't we go ahead and set up as our positive direction to match our acceleration? So let's start writing out our summation equation. Sum of the forces in the y is equal to L minus T minus 127,400, and that's going to be equal to the mass times acceleration, so that's going to be 1.3 times 10 to the 5th times 5. And again, this is just the mass times acceleration, so we're using Newton's second law here, F equals ma. This is the sum of the forces. That's going to be equal to the mass times acceleration. And so we can start working out this numerically a little bit to get as far as we can. And so L minus T minus 127,400 is equal to, and this should be 65,000. We can add the 127,400 over onto the other side, so L minus T is equal to 192, 400. Now that's as far as we can get with this particular work. And so let's go ahead and shrink this down a little bit. And now we can work on the person. So now we draw a summation equation for the person. The sum of all forces in the y is equal to the tension, which is again going up, so the up is still positive, tension minus 490, and the person is also accelerating upward, so that's going to be equal to 50 times 5. So now when we work out the math here, we have T minus 490 is equal to 250. And so we add the 490 to both sides, so T is equal to 740 newtons. So we know the tension in the cable is 740 newtons. Now we can plug this in over here, so we can say the lift minus 740 newtons is equal to 192,400. So we add that to both sides, and so we get a final answer of the lift is 193,000 newtons, and that is with the correct number of significant digits. So for this problem, we had to use two free body diagrams for two different objects that were connected.